Good morning, friends. This is a week number 2, and we are going to do the experiment number 2 from the lab manual MCET214 heat exchanger, updated in 2022. Investigation of law of thermal conduction. So, what is the law of thermal conduction? What is the name of the law of thermal conduction? So, we have three modes of heat transfer. So first important mode is a conduction, second convection, and then radiation. So conduction is a heat transfer through metal solid is called conduction. Convection, heat transfer from one point to another point through the medium, maybe liquid, maybe fluid like gases, air or water. Then heat is transferred, that is called convection. And radiation is heat transfer from the object to any place, anywhere, by the electromagnetic waves. It is called radiation. So in conduction, we will do the first experiment, the law of conduction. So what is the law of conduction? If you have the material, any material, suppose this is a circular slab. This is a circular slab like this. If you see from the top, it looks a circle and it is having diameter. Suppose heat is flowing through this. Any heat, Q, is flowing through this. So this circular area is called cross-sectional area or heat flow area or heat transferring area. So it is flowing towards down. So this is called hot phase and this is called cold phase. So heat will come out. So here we'll get temperature T1 and here we'll get temperature T2 and this is the length X. Suppose this is the length X. Then Fourier law states that Fourier's law states that Q, heat transfer through this metal rod, is proportional to the flow area and the temperature gradient dt by dx, change in temperature with respect to the distance x, or change in temperature and the total length. And if you remove the proportionality constant, there is a called K A dt by dx. So this proportionality constant is called thermal conductivity. And if you see the unit of thermal conductivity, the heat transfer is always in watt. So I don't know the K. The area is meter square. The temperature is degree centigrade and length is meter. So this meter will get cancelled with this meter square. So the unit of thermal conductivity is watt per meter degree centigrade. So this property depends on the temperature. So this is a property of metal and it depends on the temperature, it depends on heat, it depends on the area. So as temperature increases, thermal conductivity increases. This is the formula. This formula is called Fourier's law of heat conduction. And here we need to prove that formula. So to prove that formula, we have to take a known material. So this material is a brass. And if you Google it, the thermal conductivity of brass is around 128 watt per meter degree Kelvin. And if you calculate thermal conductivity, K is Q by A dx by dt. Okay, so Q is heat flow, this is area, length and temperature. So if you calculate by this formula K and if you get your answer around 120 to 130, 140, then we can say thermal conductivity of brass by calculation and standard value from the table, it is same, then we can say Fourier's law of heat conduction is verified. How to plan our experiment? So my target is to find out K. My target is to find out thermal conductivity. So to find out thermal conductivity, what I need? Q. So how I can find Q? How I can find area? How I can measure dx? How I can find temperature? So we one by one we have to study. So we'll come back to our objectives. So from the equation, I can write the objectives. The blank report and the lab manual is uploaded on the blackboard. So first, write your name, write student ID, course code, write your section, experiment number 02, and now title of the experiment is investigation of law of thermal conduction. Law of thermal conduction. So this is the title of experiment. And now objectives. How we can write the objectives? Number 1, to find heat flow rate through metal slab. Number 2, to find temperature distribution through metal slab. Number 3, to find out thermal conductivity of one material. And to verify Fourier's law of thermal conduction. So these are the objectives you can write from the lab manual also. The equipment description and specification. So there are 3 metal slabs. First metal slab, then there is a intermediate metal slab, then there is another metal slab, third metal slab. So at the top metal slab there is a heater through which current and voltage is flowing. This is a current and voltage. You will get Q. You will get heat flow. So this is one of our objective, heat flow, Q. So heat is flowing in this direction. So that's why it is called linear heat conduction. Here there is a water cooling through which water is flowing at a rate of 1.5 liter. This is a volume flow rate. We need to adjust the water flow rate. Okay. So when you start the switch, this heat will flow in this direction and it will taken out by the water. Now, as per Fourier's law, Q is equal to Ka dt by dx. So I know Q. Now I need to find area. So this is a circular in cross section. The diameter of this slab, metal slab, is given as 0.025 meter. So we can find area is equal to pi by 4 d square. We'll get meter square. So area is done. Now temperature at respective distance. So there are 5 thermocouples. One is here. This is temperature T1. It will give you temperature T1, T2. Okay. Now temperature we can measure. So delta T is measured. Now X, distance. So this distance is given in the lab manual. Yes, there is a mistake here. This is 0.015 as it is given. The distance between each thermocouple is 0.015. And the distance between thermocouple T3, T4, T5, T6 is this. I will explain this in the diagram. Now here. The distance between temperature T1, T3. So from the surface to this is T1 is 0.0075. Then distance between each thermocouple is, this distance is 0.015. Again same 0.015. Then and again from here the same T3 and T4 0.0075, 0.0075. Okay, so total this is 0.015. So same 0.015. Again here, if you make this like above 0.0075, 0.0075 means 0.015. T6 and T7. T7 0.00015, 0.015, this distance. And again from here to here 0.0075. Okay, so these distances are given. So we can measure the temperature and we can measure the distance. We can find out K. So this is a made up of brass. brass and brass. So these all are brass, and the thermal conductivity of brass is 128 watt per degree centigrade. Okay, so this slab, metal slab, is near to the heater. That's why it is called hot section. It is near to water. That's why it is called cold section. In between hot and cold section, this is called intermediate section. Hot section, intermediate section, cold section. What is T1? T1 is the high temperature in hot section. T2 is mid temperature in hot section. T3 is low temperature in hot section. Same T4 and T5, low and high and low temperature in intermediate section. T6, T7, T8, high, mid. Now we can
cold section. Connect this thermocouple. So this is a blue color, and the number, you can read the number here, and the blue couple for number 6. Then this thermocouple, there is a color here, you can see, and last, because there is no ring here, so this is a gray color, and it is number is written here. You can see this is a gray color, and I connect, and the intermediate this. Okay, so T3. Now another, this is a brass material. Diameter of this brass material is given in the lab manual. It is at 0.025 meter. So I know diameter, I can find out area because heat is flowing like this. Okay, so this dimension is given to you in the lab manual or in the question. We need to find area. So cross flow area is this. So this thermocouple and this thermocouple, and there is a slot here, projection and slot. So check. If you put like this, it will not fix, but put like this, yes. So this projection will go inside the slot like this. Okay, now this thermocouple is connected to 4 and this thermocouple is connected to 5. Okay, then this is called hot section, where there is a heater. This is called hot section, where there is a electric heater. So voltage and current here coming. So voltage and current means Q. Q is equal to VI. It will become hot. That heat is flowing through this slab. Okay, so I can measure the temperature T1. Check the number here, number 1. It is connected to number 1. Check the number here, number 2. It is connected to number 2. Check here. And number 3, it is connected to number 3. So keep this, there is a projection here, keep it here like this, fix. Then keep this locking system and then press it. Okay, sometimes there is a thermocouple, thermopaste available. You can put the paste here. All you can make the contact. This will reduce the contact resistance. So you can use the thermal paste. But we don't have thermal paste to put it here, so no problem. Okay, now what is the first step? Make the setup ready. Connect all thermocouples to respective position. Connect all thermocouples to respective thermocouple slot. Okay, second step. This is a water outlet. Okay, start the water outlet. This water bottle, how much it is written? 600 milliliter. Okay, less than 1 liter. So I need to maintain the water flow rate 1.5 liter Coca-Cola bottle, 1.5 liter in minute. So this is half, 30 seconds. 25 to 30 seconds, this will be filled. I need to adjust the water flow rate. It's not important, but approximately, if you check, this is 1.5 liter per minute. You have stopwatch. Can you start the stopwatch? 1, 2, 3, start. Stop. How much? Yeah.
25.
See, our guess is very good. So why I told you, no need to measure. No need to measure. Just like this. 1.5 liter per minute. Now start the water. How to write now? Start the water at a rate of 1.5 liter per minute. Next, make sure this power switch are on. So this is off now, make it on, up. Okay, so this is a trip, it will off. Now third push, third finish. Now power switch on, then another main power switch on. Okay, now you can see here, this is knob on voltage and current. So I need to record voltage and current. So what is the voltage now? 1. So I will give you 3 voltage. 1, 2, 3, 3 readings, or 2 readings. 2 readings enough. We will take 2 readings. First 9 volt and 12 volt. So first I will adjust this to 9 volt. How? Increase this, turn this and make it 9 here. Say 9 volt. 5, 6, 7. 9 volt. Okay, 9.1, 9.2, nothing, no problem. Whatever you display, you write. Okay, around. So set some voltage, 9 volt, and then measure the current. Okay, so what I need to write? I need to write voltage, what is the current. Then what is T1? So keep this on T1, T2, T3, T4, record here T5, T6, T7, T8 after steady state is reached. What is steady state? What is steady state? Keep it on T1 always. So this will increase and then heat is flowing. This is T1, T2, heat is flowing downward. So you can see T1 increase. Put it on T2. T2 will also increase. Like increase, increase, increase. Then like this increase, increase, increase and become steady. There is no change. There is no change in temperature with respective time is called steady state. So when the system reach steady state, means there is no fluctuation in number, record the readings. It will take a long time. So our lab is 3 hours. I will not wait. Okay, we will wait for at least 15 minutes. So I will explain there. So after 15-20 minutes, you take reading. Then come here, increase voltage to 12 volt. Then wait for 20 minutes and then record the readings. Got it? Now keep this on 21, 22. If there is no change, then we can record all the temperatures. Now if you see this T1, T2, T3, if there is no change for at least 1 minute, then we can say steady state is reached. Okay? Okay, thank you. Now we will explain the remaining things.
So we can go to the lab manual, lab report, and as I told you, equipment description, draw the diagram here and write all the what I wrote there, experimental setup and procedure. I will tell you the procedure now, and you can write from that. You can see the video and you can write from there also. Now, observation. Observation you should write from the lab manual. It is given here. Yes, these things you need to write. Okay, these things. So I will simplify this and I will write here. Number 1, the important observation is diameter of metal slab is D is equal to 0.025. Number 2, the distance between each thermocouple is 0.015. Number 3, distance between face of slab and thermocouple is 0.0075 meters. That I explain in here in the diagram. So this is a face and this thermocouple distance 0.075. Number 4, important, the thermal conductivity of brass is K brass is equal to 128 watt per meter degree centigrade. So this is the observations I took from the lab manual. And now observation table. So what I am going to observe now, as I show in video, the voltage is given to you, or we need to select the voltage 9 volt, 12 volt, 15 volt. Then wait for 20-30 minutes, that is until steady state is reached. So how I know steady state is reached? So keep on temperature T1 or T2, and if there is no change in T1, it remains constant at least for 1-2 minutes, then we can say steady state is reached. Then record the readings.
How much current?
I don't know.
0.96.
Yes.
Temperature T1, how much?
48.3.
44.6. 14.9. 38.9. 31.4. 29.7. 26.8.
Keep it on T1 back again. Keep it on T1. Okay. Yeah, 1 minute. Keep it on T1 and increase the voltage to 12 volt.
12?
Increase the voltage to 12 volt. Turn the circular.
12 voltage.
Turn it.
Oh, دقيقة.
Yes, 9. Yes. Okay.
Okay.
Now, after 20 minutes, we will take the readings. Okay.
Okay.
Yes, stop. Now see here, temperature 48, 46, 44, 40, 38, 31, 29, 26 is decreasing. Means we are correct. If some temperature is increased or shows like 26 here, means thermocouple is not working. Okay. Now I replace all thermocouples and all are showing correct reading. So these are the correct and latest reading, today's reading for the experiment. Okay. Now after 20-30 minutes, we will record the readings for 12 volt. We will not take 15 volts, only 9 and 12 volt enough. Okay. Thank you.
So what is the first record? We need to record the current. The symbol is I. The unit is ampere. Hot section, temperature T1, high temperature. The unit is symbol T1, degree centigrade. Then hot section, mid temperature T2. Then low temperature in hot section T3. Then intermediate section, high temperature T4. Then intermediate low temperature is T4, T5. Then cold section, high temperature T6. Mid temperature T7, and low temperature T8. So same this in cold section, right cold section here, right hot section here, right hot section here. Don't do like this. From the equipment, take the readings and write the data after steady state is reached. So record the readings. The voltage current is 0.96. Now we'll move to the calculation table. Now again same particulars. So we'll do the calculation also. As per this law, I will explain the calculations. Sample calculation. Result and discussion, sample calculation. I will write the formula and we'll write the flow chart here. So Q is equal to Ka dt by dx. So I need to collect one by one. So I need to find K. So first I will find the area is the simplest. So heat flow number one. Heat flow area, cross-sectional area is equal to A is equal to pi by 4 d square. Now, second, I can find out heat flow through the slab. Q is equal to voltage into ampere. So voltage is 9 volt into ampere is 0.96. I have 3 sections, so I will find the temperature difference in 3 sections. So number 3, temperature difference in hot section is equal to delta or delta T 1 to 2 or 2 to 3 or 1 to 3. I can choose any one and I can write the formula. It is up to me. If I choose 1 to 2, T1 minus T2. So I choose T1 minus T3. Okay. So 2 to 3, 1 to 3, whatever you can choose, any one. Okay. So T1 and T2, you can put the values. Similarly, I can find out temperature distance in intermediate section. Delta T 4 to 5. Check thermocouple 4 and 5 as I explained here. 4 and 5 in intermediate. So here T4 is, similarly I can write number 5, the temperature difference in cold section. Cold section here also delta T 6 to 7, 7 to 8 or 6 to 8. So I will choose 6 to 8. So T6 minus T8. So once I know temperature difference, colors say now. Here I know Q, I know area, I know delta T. Now delta X already I know, so I can find out K. So number 6, thermal conductivity of metal in hot section. So I will write K hot is equal to Q by A is not change, dx by dt. Okay, so I will write Q by A delta X hot section 1 to 3. So I will write delta T 1 to 3. 142.7 watt per meter degree centigrade. Similarly, I can find for intermediate section thermal conductivity of metal through intermediate section. So K intermediate, K int is equal to Q by A delta X 4 to 5 divided by delta T 4 to 5. One 31.9 watt per meter degree centigrade. Similarly, 8, thermal conductivity of metal in cold section, that is called K cold, is equal to Q by A delta X 6 to 8. You can choose 6 to 7 also, no problem. Delta T 6 to 8, because I calculated 6 to 8, I will choose 6 to 8. And your answer is 114.7 watt per meter degree centigrade. So this is the thermal conductivity, and now see, as per observation, we wrote 128. So this answer is in the range. Then we can say the Fourier's law is verified. See, these 3 answers are same. So now I will come to the calculation table and I will fill the data here. Now, as I told you, I calculated area. Now I will not write area. Now I will write symbol is Q, unit is watt, and it is 8.64. Now temperature difference in hot section, delta T 1 to 3 degree centigrade. You can transfer the answer 3.7, 2.0 and 4.6. Thermal conductivity, hot section, K hot, K int and K cold. So this is similar to the what is given in the observation table, but we created from the dimension. So this is same thermal conductivity in intermediate section, and this is same thermal conductivity in cold section. So no need to write formula here, no need to write area here, so we'll keep this blank, no need here. The thermal conductivity of hot section is watt per meter degree centigrade. Here we can write the thermal conductivity of brass is around 128 watt per meter degree centigrade. So Fourier's law is verified. And another, as temperature increases, the thermal conductivity increases. See, this is cold region, intermediate hot region. The thermal conductivity increases. Now result and discussion. That is a sample calculation for one. Now similarly, write the readings for 12 volt after 20-30 minutes.
Change the current and tell me the current.
1.26.
1.26. Again?
1.26.
1.26. Okay, now keep it on voltage.
Voltage.
Yes. And now temperature T1, T2 fast, huh?
Okay.
T1,
66.5.
66.5. T2,
63.3.
next.
T3. 60.
60,
Yes.
next.
52.1.
52.1, next.
48.9.
48.9, next.
35.7.
35.7, next.
32.6.
32.6, very nice. Last.
27.7.
27.7 degrees centigrade. Last. No need to adjust now. Now at last, make the voltage 0. At last, make the voltage 0. Turn it to 0. Fast, fast, no problem, no worries. Fast. Yes, until the end. Make it 0. Until end. Yes, it stops. Yes, khalas. Okay, now switch off. Yes, it is still there. Now it is 0.00 voltage. Okay, and now main switch off. And when you leave the lab, close the water. Okay, if I didn't close the water, next teacher will complain to me there. Okay, so remember, at the end of the experiment, you need to close the water. Okay, so let it cool little, and then we can make it close. 15 no need, only.
Write the second readings for 12 volt. You can write the current is as we take the readings. So no need of for 15. So do the sample same calculation for 12 volt and write your answer here. Now we'll go to the graph. Temperature distribution versus distance. Now you can use this graph as it is, or you can take the ready-made graph that I will show you, 0.5 degrees centigrade, or you can make 10 lines. Instead of this, you can make 10 lines is equal to 5 degrees centigrade or 10 degrees centigrade, and here is 0.01 meter, one line, 0. Okay, so one line, 10 line is equal to 0.0. So instead of, I can count the 10 lines, 1, 2, 3, and I will make it 1. So here it is already there. So this is 1, 2, 3, 4, 5, it is there, 6, 7, 8, 9, 10, it is there. Okay, so we'll make this as thermocouple 1. So where 1? T1. Here it is a T1. I will make it T1 here. So distance of T2. So T1 is here. I make it T1. Okay, add 0. So T2. The distance between thermocouple T2 is T1 and T2 0.015. Okay, so here I will mark T2. 0 plus 0.15 is equal to 0.015. Okay, so I will make a line at 15. So this is 0.115 is near center. So I will make this is for T2. I will draw this later on. Okay, so this is T1, T2. Now T3 again 1.5. So here T3. The distance between 0.015. So T3 will be at this 0.03. Okay. Then after T3 there is a separation of the metal from here to here. So 0.075. 0.0075. So here plus 3 is 0.0375. Then again there is a gap 0.0075. We'll get here addition of these two will get T4. So 0.0375 plus 75 is 0.045. Okay. So then distance between T4 and T5 is 0.015. So the addition with this addition is equal to 0.06. Like a table of 15, 30, 37, 45, 60. Now there is a metal rod slab. This is metal first slab, hot section. Now this is intermediate section, 0.0075, 0.0075. So 0.0675 is equal to, and then you will get here T6. So we'll get here T6 plus 0.0675 plus this you will get here 0.075, and then T6 and T7 again 0.015 you will get T7. T7 is 0.09. Again T8 the same distance 0.015, so it will become 0.105, and then again 0.0075 your material finish. Okay, so I need to plot this at the different line. Now I plot at T2, so it will be at T1. This is T1, T2, and now at 3 again here. Okay, so this is 1.5, then 3, then 3.75 here. This is the end of material. Okay, so this is the end of the material, 3.75 somewhere here, 4.5 in between here, 1, 2, 3, 4, 5, 6 here, another thermocouple for intermediate. Then 675. So this is 675 is somewhere here. It finish the intermediate section. Now start the code section. 675, 0.75. This is 7 and 0.5 is here. 75, 9, 8. This is 9. 9.9 and 8, 10.5. 10.5 is here. 10.5 is here. Okay. So this 10.5 is in between 10. The minimum temperature is 26.8. So I can start from 20 degree. So this is 20 degree. This is 25. So I can mark it here. So this is 25 degree, 30 degree, I can write here 35 degree, 40 degree, 45 degree, 50 degree, 55, 60, 65 and 70. Last temperature 16 for 12 volt. Now I will plot the temperatures. So 48.3, this is 40, 48 and second line. So this will be the, so I will write here, this is temperature T1, T2, T3, T4, T5, T6, T7, T8. Okay, so first temperature is 48.3. So 48.3, this is here. Then second 46, 45, 46, two line here. Two line is 1 degree. Okay. Then 44.6, so 45, 44 means two line less. 44, one line less, 44.6. So one line less here. Okay. So T1, T2, T3, T4, 40.9 means this is 40.9 means one, two lines. This is 40, 40.9 is here. Okay. Then 38, 50, 38 means this is 35, 38 is here. Four lines before 40. Then 31.4 T6, 31.4, so 30 is here, 31, two lines and one line, three lines, T6, 29, T7, 29 means two line less, one line less, 29.7 because one line less, and 26.8 around 27. So about this 25 and four lines, four lines here. So draw these first 3 points by the straight line for hot section. Yes, this will be a straight line. Then for intermediate section, this 2, and for cold section, this 3, and join these 2 points like this, like this. So similarly draw for 12 volt. So 66.5, 66 here, 65, two lines, 66 and a half, one line. Okay, T1, T2, 63. Same way, join the lines by straight line from 1 to this, then, and then from this. And join the, now you go to the report, writing conclusion from the graph is little. For 9 volt and now 15 volt, I will cancel it. There is no 15 volt. So 9 and 12. So 9 and measure the temperature gradient to hot section for 9 volt dt by dx. So how I get this for 9 volt and 12 volt, I will explain here with the help of graph now. Now here, one curve for 9 volt and this is for 12 volt. Okay, so I need to take the slope. So I will choose any 2 points. I can choose here, any two point in hot section, cold section, and intermediate section and cold section on the 9 volt curve. So I can choose 1 and 2 or 1 and 3. So whatever I did in sample calculation, I will get the same answer. Or I can choose 2 and 3. So I will draw the vertical line and I will draw the horizontal line. From this point, I will draw a horizontal line. And now this is dx delta x is equal to 0.015. Distance between two thermocouples, this and this, is dx, and this temperature difference is dt. This is dt. So how much dt? T2 minus T3. So T2 minus T3. So this is a 46.6 and this temperature is 44.6. So dt is equal to 2 degree. So I can get it here. dt is same way for 12 volt. I can choose here 2 points, one and this, and I can write the difference here dt and this is dx. So I can write here dt by dx. Okay, so goes on repeating for 9 volt in a intermediate section. Now in intermediate section, so you can draw same, choose any 2 points in the intermediate section. So you can choose 4 and 5 here, this point and this point. So write dt, that is T4 minus T5, T4 minus T5, check the temperature and write dx, it is same. So here I can write with a scale. So you can write for 12 volts, no 15 volts. So for 9 volt in cold section, you can do it same way in the cold section. So in cold section, you can choose any 2 points. I will choose this. I will choose this. This is dx and this is dt. So dt is T6 minus T7. So I can write here. Same here you can do, cancel 15. And from the graph, for 9 volt dt by dx, whatever the answer you got here, this answer you can transfer here and put q whatever there as per calculation and you can complete this. So conclusion, you can write K brass is equal to 128 from table and calculation is approximately same, hence Fourier's law is verified. Number 2, as temperature increases, thermal conductivity K of material increases. So this is the end of the experiment. At the end, clean this equipment and close the water and switch off the machine.